All right, my Algebra 2 students, hello, Mr. Alent here. We're going to go over our Unit 10, Section 1, which actually corresponds to Chapter 13, Section 1 in your textbooks, which covers trigonometry. And this actually is a little bit of a review from last year. For all of you guys who were in geometry last year with us, we did right triangle trig, and that's what we're going to get into right now, some right triangle trigonometry. We'll see those functions, sine, cosine, and tangent again. And then we'll also add in actually what are called their reciprocal functions here in a little bit. This says it's the day one notes. You know, back in school we would take a couple of days to go over this. We're just going to try to knock it all out here at once. And so a trigonometric function is a function whose rule is given by a trig ratio which compares the lengths of two sides of a triangle. And the Greek letter theta is, so that's the symbol theta, is traditionally used to represent the measure of an acute angle in a right triangle. And the value of trig ratios depends on theta. And so the sine, if you guys remember, the sine function is the sine of an angle is always the ratio of the length of the leg that's opposite that angle to the length of the hypotenuse. Okay, and then there's the easiest way to do that. Sine of theta is the opposite leg over the hypotenuse. Cosine of theta is the ratio of the length of the adjacent leg to the hypotenuse, right? So adjacent leg to hypotenuse. And the tangent of theta is the ratio of the opposite leg to the adjacent leg, opposite to adjacent. So when we're doing these, if you remember from last year how we start every single trig problem starts the same way. And how do we start? We take the angle, so right here, here's theta representing this angle, and you identify the three sides. Our options are the opposite leg, the adjacent leg, and the hypotenuse. Now the hypotenuse should be the easy guy because that's always the one that's across from the right angle. Across from the right angle is the hypotenuse. Okay, and right now it's called hype in here. I'm actually just going to always use H is what I'll use, just faster. Okay, so the hypotenuse is there. Now, the leg opposite and the adjacent, now the legs, remember the word legs in a right triangle talks about the guys that are making the right angle. So this side that's marked with a 3, that's a leg. The side marked with a 4, that's a leg. So which one is adjacent and which one is opposite? Well, just like, you know, if I was on opposite rooms, you know, opposite ends of the room with somebody, that means we're as far apart in the room as we can be, right? I'm in one corner, they're in the exact opposite corner. It's the same idea here. The opposite leg is in reference from the angle. So the furthest leg from the angle is the one over there. That's the opposite leg for this triangle, or at least for this angle in this triangle. And I'll just, again, use O for that, for opposite leg. And the adjacent means next to. You know, if you're talking about like houses on a street, adjacent houses are houses that share a property line. They're right next to each other. And so it's the leg that's adjacent or sharing side with the angle. And so this side right here with the 3, that is our adjacent leg. Adjacent leg, and I'll just be calling it A from now on. So that is how you begin every trig problem. Identify O, A, and H. Okay, the opposite, the adjacent, hypotenuse. And again, I usually start with hypotenuse because that's the obvious guy. It's always across the right angle. And then from the angle we're talking about, either you're given or you're looking for, you're going to then identify O and A. And O and A switches. You know, if this was the angle we were talking about, then this would now be O, and that would be A, right? So it is dependent on the angle. Okay, and if you remember, we had that acronym that we always use to help us, you know, to kind of explain what we have going on with these, help us memorize. And that acronym was SOHCAHTOA. All right, do you guys remember that? SOHCAHTOA. So sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Exactly what we see right here, just in a quick, you know, it's really easy to remember SOHCAHTOA. When I say that, everyone's like, oh, yeah, SOHCAHTOA. Okay, so let's see a couple of quick examples here. It says, find the value of the sine, cosine, and tangent functions for theta. So here's theta. All right, we're going to look at example 1. Sorry, my printer decided to do some stuff, if you heard that noise. Here's our angle theta, and I always kind of mark it, you know, so that I know where I'm kind of working from. Again, we start by labeling the sides, right? So directly across from the right angle, that's our hypotenuse. The one directly across or furthest away from the angle is the opposite leg, right? Opposite sides. And then the leg that's closest, right up coming into it, is your adjacent, OA and H. That's important because then that tells us how we're going to build our ratios, right? So find the value of the sine, cosine, and tangent functions for theta. So we're going to go ahead and complete this out here. So for the sine of theta, again, that's O over H, the opposite over the hypotenuse. The cosine of theta is the adjacent over hypotenuse, A over H. And the tangent of theta is the opposite over the adjacent, O over A. And so now we're just substituting in, guys. We're just looking in the picture here. So for sine, we're going to go O over H. O is 15, H is 39. 15 over 39. For cosine, A over H, 36 over 39. And then O over A, 15 over 36. And there you go. And guys, these are decimals, right? If I were to go ahead and divide, well, let's just do it real quick. In my little calculator here, right? If I divide 15 by 39, you get some decimal. And when you punch in a number into your calculator and you say, like, you know, I don't know what this angle is right now, we could solve, actually. It'd be really easy to do using some trig stuff right now. But I haven't done it. But you would, you know, if we knew what this angle was, we would hit sine of, let's say it's like 25. I don't know. I'm just making that up. And let's say sine of 25. Let's just punch it in. Sine 25. You get some decimal number. And sometimes we forget what that decimal number represents. It represents some ratio, guys. These are what are creating these decimals that you see. And it's all because of similar triangles. Because for any triangle that has these angles, they're going to have this ratio of sides. It's always going to be the same. Now, they may not necessarily be this length, but the ratio of them will always be the same for every right triangle that has the same sets of angles, okay? Which is why the sine, cosine, tangent stuff even works, and why the sine of 25 is going to always have this ratio for its opposite to its hypotenuse. All triangles with the angle of 25, okay? Let's go ahead and look at the next example. Again, start the same way, right? We're going to identify the sides. So opposite the right angle is the hypotenuse. Opposite the angle of reference, the angle we care about, is your opposite. And then the side that's coming right into the angle is your adjacent. So there's our OA and H. Okay? And same story, we're going to set up our three functions. Sine of theta, cosine of theta, and tan of theta. And I'm going to go ahead and skip the OA and H stuff like you can see here. You know what we got to do, right? So sine theta is O and H. O and H, 30 and 34. That's the ratio. Cosine of theta, A over H, 16 over 34. And tangent of theta, O over A, 30 over 16. Okay? So there you go. And back over here, if we wanted to circle those in, those are our ratios. Okay, so that's just a quick refresher on trig. And then, of course, we had like, hey, if you're solving for missing side or solving for a missing angle, which we'll get into some of that here in a minute. Something else we did last year, too, is we talked about special right triangles. The special right triangles are the 30, 60, 90 triangle, and that's just in reference to the angles. It's got a 30-degree angle, a 60-degree angle, and a 90-degree angle. And then we also had the 45, 45, 90 triangle with two 45-degree angles and a 90-degree angle. So this is an isosceles triangle, right? If you got two angles the same, then you have two sides the same, and it's isosceles. And so you can see the two examples here. Here's a 30, 60, 90, a 45. It doesn't show 45 there, but it's got to be 45 because the angles add up to 180 in a triangle, right? So 45, 45, 90. And the ratios are given there. So for the 30, 60, 90, the ratio of the side lengths is 1 to radical 3 to 2. Now that's kind of a weird ratio, but it's consistent, and it's true always. All 30, 60, 90 triangles have this ratio. This is the short leg, that's the long leg, and that's the hypotenuse. So 1 to radical 3 to radical 2. And you can kind of see it here in the picture. Short leg is 1, long leg is radical 3, hypotenuse is 2. Now, I'm not saying that all 30, 60, 90s have those side lengths, but the ratio of all those side lengths will always be 1 to radical 3 to 2. And that's how we can apply and know this. This is why we call them special right triangles. we don't get some random, remember, go back to here, some non-terminating, non-repeating decimal when we do a sine or a cosine or whatever. With these, we get this nice ratio that we can see. If we do the sine of a 30-degree angle, it's 1/2 always. I mean, I'll do it right now. Sine 30. It's 1/2. Boom, even the calculator knows it, right? So that's why we recognize these and call them special right triangles. It's just because they have these nice ratios. So the sine of 30 is 1/2. Again, because go over here, right? Here's the 30. Sine is opposite over hypotenuse. Opposite over hypotenuse, 1/2, right? So with a 30, 60, 90, the short leg is always half the length of the hypotenuse, right? 1 is half of 2. So if this particular 30, 60, 90 had a hypotenuse of 10, this guy would have to be 5. It has to be half of that, okay? And then the long leg is always, really, it's the short leg times radical 3. So this would have a length of 5 radical 3. So it would be 10, 5, and 5 radical 3. Okay, we'll get into some examples and see that shortly. Cosine of 30, right, radical 3/2, adjacent over hypotenuse. The tangent of 30, opposite over adjacent, 1 over radical 3. But remember, back long ago when we did rationalizing the denominator, when we were working with radicals, we don't keep the radical in the bottom, so we have to manipulate to get the radical out of there, and it simplifies to this, radical 3/3. So these three are the common sine, cosine, tangent for 30, a 30-degree angle. For the 60, it's just new reference angle, opposite over hypotenuse would be radical 3/2. The cosine, there's your 1/2, because this is now the adjacent, 1/2. And then for the tangent of 60, that's a radical 3/1, which is just radical 3, right? Something divided by itself is radical 3. All right, the sine of 45. Now with the 45, again, notice that they're 1, 1, radical 2, right? It's isosceles. These are both 45-degree angles, so these are both the same length. And it's 1, 1, radical 2 is our ratio. So the sine of 45 would be 1 over radical 2. Again, we rationalize our denominator to get radical 2/2. Well, the cosine of 40, it's still the same one because it's isosceles, so they actually are equal. The sine of 45 and the cosine of 45 are exactly the same, radical 2/2. And then the tangent of 45, that's kind of a fun one, because then you're just going to have the same number over itself. 1/1 equals 1, right? Okay, so we'll see how to maybe apply those here in a moment. The important thing, though, is if you don't remember the rules and all this that I just showed you, trig. Use trig. Trig works. If I were to apply trig to a problem with a 30, 60, 90 or a 45, 45, 90, I'm still going to get those values anyway. Okay? So let's see. We're on to problem 3 here. I'm getting a little short on time, so you know what? I'm going to end this video here, and then we'll pick it back up here on the next video. So we'll have to break this into 2 parts. So that was the part 1. Next will be our part 2 on actually then applying these. So be back in a sec.